Hi, now let's discuss about diffusion further with a micro and macroscopic scale, so-called a Fick Law of Diffusion. So previously we discussed about the random walk concept. So let's discuss about macroscopic diffusion. It's called the Fick's first law. And let's see, we're discussing about at the steady state, which means the concentration of in space will not change over time. So let's consider this a hypothetical, the number of particles and hypothetical area in space. So with the expressed with the dotted line. And we are interested in how these particles of our interest pass through this area. That we want to define the concept of flux, which I already talked to you before. So for diffusion is in the spread of this particle. So we want to describe it with the area here. So we want to count the number of particles through this area per unit area and per unit time. And this general concept is called flux. So the rate of diffusion or flux. And we use a capital J. And that is from observation by Fick and his understanding. This flux is proportional to the concentration gradient of the solutes. And here we are discussing about these dots as a solute molecules. So the flux is the number of molecules that pass through this an imaginary plane per unit time per unit area. So flux is number of crossings of physical entity per unit time per unit area. And however, thinking about this, depending on how we define the area, the flux might change. So the flux is in fact a vector quantity which having a direction and the magnitude. So that's important concept. And if the sign of this is whether towards a high or lower concentration. So look at this, for example, at the point of x equals 0 is concentration of C1, which is higher, and x equals delta x, the concentration is kept low as a C2. Then we know from our experience that particle or solute will likely to overall move from left to right. So that's the direction. So here, in this phenomenon, we define the diffusion coefficient already, and D is a proportionality constant. And from previously, the unit of diffusion, we remember that the diffusion is, the unit is length square over time. So that's typically we use a centimeter square over second. So it's good to know the typical diffusion constant in water for like oxygen, very small molecules, it's usually 10 to the minus 5th centimeter square per second. If the particles are bigger, such as proteins or DNA, larger molecules have much harder to diffuse. So it has 10 to the minus 7 square centimeters per second. So this equation of flux is proportional to the concentration gradient dc over dx, and we want to put the proportionality constant as a d, which represents diffusion coefficient, and the minus stands for the flux will happen from high to lower concentration. So how we can, this is kind of intuitive, let's try to derive this. So later on. So diffusion coefficient, again, let's remember that root mean square of displacement from a random walk. So x square mean and then square is proportional to square root of 2 dt. We put 2 there, remember when we derive this from random walk, and full derivation is in this reference too. So what does this diffusion coefficient mean? is characterization of the migration of particles of a given kind in a given medium at a given temperature, which means diffusion coefficient is a function of kind of particles and the medium and the temperature. So it's interesting to see what this diffusion will do for us for the transport of small molecules, especially inside the cell. So here's a question. For a small particle with diffusion coefficient of known, so it's like oxygen, carbon dioxide, and those have 10 to the minus 50 centimeters square per second, what would be the time to diffuse a distance within a bacterium? You know that bacterium has about length scale of 1 micron. Or let's consider if there's a 1 millimeter of a space in assuming one-dimensional problem, how long does it take for the solute molecule from one to the other end, which is about 1 millimeter? So that's the question, and we will move on to the next step. So let's discuss about the diffusion time in a bacterium or in a cell. So let's see, some previously root mean square of in X one-dimensional diffusion as a, so root mean square is defined as square root of 2 times diffusion T. So let's see here. And let's first consider about a bacterium, which has a length scale of, as I told you, about 1 micrometer. And 1 micrometer in terms of centimeter is a 1 micrometer, 10 to the minus 6 meter, 10 to the minus 2 meter is 1 centimeter. So this is 10 to the minus 4 centimeter. So then from occasion 1, we know that square root of an average is 2d tau, or so the time constant t will be this x squared over 2d. And let's input here, so square. So this is 10 to the minus 4 centimeter square over 2 times 10 to the minus 5 centimeter square over time. And guess what? What time would it be? It's half a millisecond, 0.5 millisecond. So, you know, inside the bacterium, a solute particle to move around till the end, it takes only about half a millisecond. That's pretty quick. So second, as from the example for distance of L equals to 1 millimeter. So for 1 millimeter, which is tiny, but for cellular aspects, it can be pretty big. Then let's say that tau, let's say that tau 1 millimeter. Likewise, we can do the same way. 1 millimeter is 10 to the minus 1 centimeter square over 2 times. Likewise, and then guess what will happen? It actually is a 500 seconds. Wow, it takes so long time to move the particle from one to the other 1 millimeter away. And it takes 500 seconds. That's pretty ineffective. Then let's move on maybe for a cell. So cell size, typically we can consider it as about a 10 micron scale. So let's put a 10 micron. So tau over cell, now it's a 10 micron, 10 to the, so 10 to the minus 3 centimeter square over 2 times 10 to the minus centimeter square over second. And guess what? What will happen for this? Yeah, the cell, let's see, this is minus 10 to the minus 6 plus 5 times 0.5. So that's a second. So 0.05 second or 50 millisecond. So which is not bad. So inside the cell diffusion time still is about 50 milliseconds. That's pretty short. But now we understand that, wow, that small scale of 1 micron and 10 micrometer bacteria size or cell size, maybe this diffusion is effective enough because it takes only about, half a millisecond order to tens of millisecond order to move around. So here, now we know the answer of a small particle to diffuse a distance of a bacterium, 1 millimeter, or a cell. So this takes about 0.5 milliseconds, very effective. However, we realize if the distance is getting larger and the time will take much longer. From here, we actually know that if the distance is about twice, for the distance to RMS distance to be twice, we realize there's a square root, so the time will take actually square of this, which is, in order for a particle to wander twice as far, it takes 4 times longer time. So, or twice or 10 times to move around, the time will be 100 times longer. So now what we see here is diffusion is a very rapid and efficient transport process when distances are relatively small or short. But when it becomes longer, now we realize diffusion might not be as very effective phenomenon. So the next is now discuss about derive that fixed first law of diffusion. And that will be based on this assumption and question of how many particles will move across a unit area in unit time, that's a flux, from the point X to the point X plus delta. And we want to calculate the net flux in the X direction. So now let's see, fix first law of diffusion. So this is from the random walk concept. So let's consider the flux from a point of, let's say, in X direction at X and X plus delta. In between, there's an area A. So what will be the number of particles at X as a function of n sub X? Then automatically here, X plus delta will n X plus delta. And, assume from X from lower to higher number. So the direction as a this. So this is an area. And so from the random walk point of view, what are the net number of particles crossing this in between? And that's related to concentration gradient, which was described by Fick. But let's see what happens for that. So the net number of particles crossing from here, X, because random, it can move, particle move in either X direction, the next step, or minus X direction. So the probability is half, but we are interested in this crossing this area. So that will be positive is n sub X, but that probability is half. Likewise, the particle number at X plus delta has also equal probability of moving either X or Y, minus X or plus X direction. So when we are interested in number of particles moving to the positive X direction, so if it's negative, will pass through, but that will be half of this. So 1/2 X plus delta. That is number of particles. Then let's calculate the flux. The flux, by definition, is number of particles crossing per unit area per unit time. So the flux as X direction Jx will be this the flux will be this number, 1/2 nx minus nx plus delta, okay, divided by per unit area and per unit time tau. Okay, and we usually write down an nx plus delta minus nx. So I just rearrange this, minus 1/2 nx plus delta minus nx divided by area and tau. And now, because this n is the number, we want to describe it as a concentration, which means per unit volume, number of particles per unit volume. And unit volume will be A times a, let's say this delta is delta x. So area times delta will form a nice volume. So we will use that part. So to rewrite this, like 1/2, and I like to make it a concentration. So x plus delta over area times delta minus nx area times delta, okay? And so the tau will come out here, frontal part, and then because this is can be described as a gradient, so I would love to put as a delta over here, because I introduced 2 delta or delta square, I put delta square back over here. So this is a nice description now. And this is kind of familiar to us. So how is this familiar? So remember that we have concentration, diffusion coefficient from our random walk. So we define as a 2D as defined as delta length square over tau. So let's use that concept over here. Is now minus 1/2, and this is 2D, and this is now actually concentration. So this is concentration at x plus delta, and this is concentration at x. So this defines as a concentration gradient. So that's if we write in differential form, round the c, round the x. So thus what we see is jx equals minus d round c round x. This is the description by as a Fick law. Now you recognize why I introduced number 2 for x one directional diffusion. Why I introduced 2? Because I want to make this one a nice simple d instead of half d. So now you understand. So this is the result of first law of diffusion, meaning that the number of particles flux is proportional to the concentration gradient as a proportionality constant, a nice diffusion coefficient. And we put minus because it's usually high to lower concentration.